Hello, this is a video in a playlist introduction to biostatistics using R, and we're in part 3 of basic probability concept, and we're going to look at marginal probabilities. And really, a marginal probability refers to the probability of a single event without considering any other related events, and it's derived from a joint probability distribution. And then what we do is we sum or integrate out all the other possibilities of other variables. And I think examples will help this. So if we have two events that we're interested in, or we have two events and we're interested in the marginal probability of A, but we have a joint distribution of A and B. And so the marginal probability is found by summing over or summing out the other variable. Okay, and this will, I think, will make sense when we do the example if it doesn't make sense already. And for the continuous case, we would integrate out the second variable. And since in this we're not in this we're not going to assume calculus, so we're not really going to consider this. So let's assume we have one red die and one green die. And then let R be the outcome of the red die. Okay. And G be the outcome of the green die. And we want to find the probability that the red die is 2. Now, we already know that the probability of rolling a 2 on the red die is 1/6, right? Because the two die are independent and they don't factor together. But we're going to build up this concept of summing out a variable to find the marginal probability. So this is what we're interested in. And we can think of this as the probability of 2 times the probability that the green dice is equal to 1 of the 6 occurrences. Okay, so what that means is the probability that we roll a 2 is the probability we roll a 2 and we roll a 1, or we roll a 2 and the green die is a 2, or the roll a 2 on the red die, roll a 3 on the green, and then etc. 4, 5, 6. And doesn't that make sense? So in a sense, we don't really care what the green die is because we're summing over all possibilities. Well, it turns out what's left is this marginal density. And so each of these probabilities that we roll a 2 and roll a 1, that's 1 over 36. This is 1 over 36. When we add those together, we get 1/6, which we know is what it should be. So let's create a little R program to illustrate this. And so let's create a matrix, 6 rows, 6 columns, and each entry is 1 over 36. And so this, what we're trying to do is create a matrix where this represents the green die. So it can be a 1, 2, 3 to 6, and then the red die is a 1, 2, all the way to 6. And so the probability of rolling a 1 and a 1 is 1 over 36, and then etc. for the rest. So I want to label these columns and rows, and so that's the dim names of this matrix, right? The matrix. And so I want to create the row names and the column names. And so this paste is a fast way to put an R with a 1, then an R with a 2, and an R with a 6. And so this is our matrix of it's the joint density of rolling a red die and a green die. Now, the probability that we roll a 2 is we sum out all the possibilities of the other event. And so when we sum those, we get 1/6. So to do this, we could add margins of our matrix. And then in the mass library, there's a function called fractions, which I like. It's kind of nice. And it adds these margins or the totals to the rows. And notice that they're all 1/6. And that's what it should be. So the probability of rolling a 1/6. Probability of rolling a red die and obtaining a 6 is 1/6. But it's also this way. If we want to find the probability of rolling a 4 on the green die, then we sum all possibilities of the other event for when the green die is a 4, and that's 1/6. Okay. Now, Bayes' theorem, and we're going to look at like screening tests. So if you go in and they test you to see if you have some disease, then there's nomenclature associated with those screening tests. And the ones we're going to look at is sensitivity, specificity, predictive value, positive and negative. Okay. But before we do that, let's look at some key concepts of some Bayesian methods. And this one is called Bayes' theorem. And to me, it's kind of magical. So if we're looking at the results of some test, and then D is a disease, for instance, what's the probability the test is positive given you have the disease? That's what this represents, could represent, but generically it could really be anything. And the conditional probability tells us that this is the formula, right? It's the probability of their intersection divided by the probability of D. But this here, we can use the multiplication rule and rewrite it like this. So it's the probability of P, divided by the probability of D, divided by, or times the probability of D given theta. And what's, in my opinion, is sort of magical. Look at this conditional probability. We've reversed it here. Now it's probability of D given theta. And this formula alone can help you solve some pretty amazing problems that initially you think are unsolvable. But in the Bayesian framework, this piece right here is called your prior probability, right? Because here we think of as the parameter of interest as a random variable. And so this is our prior probability going into the experiment. And then this is the likelihood. So we're collecting data under the assumption of our parameter theta, right? We had prior beliefs, so we put it there. We collect data, and we see how likely of collecting that data given our belief is. And this is just a normalizing constant to make everything, add up to 1. It makes it a density. And so what this represents is we go in with our prior beliefs, we collect data, and now we have a new belief for the parameter theta. That's kind of the Bayesian philosophy in a nutshell. Okay, and then once you've collected the posterior distribution or posterior probability, then you can start conducting confidence intervals for theta. Now, if you're a Bayesian, you don't say confidence intervals. Confidence intervals, it's a frequentist viewpoint. You call them credible intervals, but it's essentially the same way. It's analog to the confidence intervals for Bayesian. Okay, so now we're going to use this table throughout the rest of the section, and it's for possibilities on a screening test. So you go in as a patient. Now, technically, you don't know if you have the disease or not. So this is kind of a theoretical construct. Let's let D represent you have the disease. And of course, D complement means the disease, you don't have the disease or it's absent. You go in, you get a test, and the test can either be positive or it could be negative. And it creates a little 2x2 table. And so we're going to label each of these sections that it's the true positives, right? And that's a correct decision, right? You have the disease. The test said you had it. It's correct. This cell, remember it's a 2x2 table. It's a true negative. You don't have the disease. The test said it's negative, and you were correct. Now these cells are mistakes. You don't have the disease, but the test said you did. Here you have the disease, but the test said you do not have the disease. And then of course we can create row and column totals, for this table. Now the term sensitivity means for those that have the disease, how many did we get correct? Right? So it's the number of true positives divided by this total. So that's called sensitivity of the test. And specificity is the opposite. You don't have the disease and the test predicted correctly. So that it's a true negative over everyone that didn't have the disease. Okay, and now the positive predictive value is you condition this way. So among the people that tested positive with the test, how many were true positives? How many did we get correct? And that's the positive predictive value. And then the negative predictive value is from the ones that tested negative. That's what this denominator is, right? That one. How many were true negative? So these are all actually correct decisions, but thought about a little bit differently. And here, and of course, the prevalence of the disease is your total population, and then it's the number of true positives and true negatives, and that's called the prevalence of disease. Now, what I think a lot of people don't realize, these are all what are called conditional probabilities. Someone says, well, the specificity of the test is 95%. What does that mean? Specificity, it's a conditional probability. So it's given that you have the disease, what's the probability that the test indicates you do have the disease? Specificity is opposite. Given you don't have the disease, what's the probability that you test negative? Right? And then these are also conditional. Given that you tested positive, what's the probability you have the disease? Negative predictive value. Given that the test was negative, what's the probability that it's a true negative, that you don't have the disease? Okay. So really misunderstood by a lot. And so these are the definitions that we just described. And we can use Bayes' theorem to help us with some calculations. And so we can estimate the predictive positive value positive and the negative predictive value just from sensitivity and specificity. And so those are two measures that are given in almost all of these screening tests. Okay. And so this says, given the test was positive, what's the probability that you have the disease? And that's exactly what you go in. So if you were taking a COVID test, for instance, and it tested positive, you still may or may not have COVID-19, right? So we want to know, given that you tested positive, what's the probability of disease? So that's the positive predictive value. And you can back calculate it using Bayes' theorem. Now, as a reminder, this is the probability of testing positive and you have the disease divided by the probability that you tested positive. So how does this look like that? Well, the numerator uses the multiplication rule for intersection, and this and the probability of testing positive. Well, we have another event called disease. So what we do is we partition this into little mutually exclusive events that we did in a previous section, and then you can come up with these two examples. So let's say you take if a pregnancy test has 99% sensitivity and 98% specificity. Now, don't forget, sensitivity means given those that are really pregnant, the test says you're pregnant 99% of the time, correctly. Specificity says that if you're not pregnant, the test will indicate that you're not pregnant 98% of the time. Well, now let's calculate the positive predictive value and the negative predictive value. Because in a sense, this is what you want to know, is if the test was positive, what's the probability you're pregnant? Right? That to me seems of more interest. So you can create this little made up data table that satisfies sensitivity and specificity, and then we can back calculate positive predictive and negative predictive value. So let's assume we have 200 patients and we want a 99% specificity. So if we put 99 here and then divide by 100, that is specificity. Sensitivity. Dang it. So to create the 98% specificity, we have 98. We put 98 here and we divide by 100. That's 98% specificity. So that means we need 2 people here. Now to calculate the positive predictive value, which is this way. So it's the true positives and the false negatives, which is the 101, right? And 99 were pregnant. So the positive predictive value is 99%. So that I guess, I said that backwards, dang it. So I already talked about making this table such that sensitivity is 99, the specificity is 98. And now we go in and calculate the positive predictive value. I'm so sorry about that. So then what we want to know is the number that the test was positive, which is 99 and 2, right? 99 and 2, so it's 101. This is the number that were actually pregnant, so 99. So it's 90. The positive predictive value is 98%. So if you have a positive pregnancy test, then there's a 98% probability that you're actually pregnant. But we can use this using Bayes' theorem. If we use the formula that we did upstairs. So this is the multiplicative rule, and maybe I should flash. We're using this to find the positive predictive value. And I'm not going to go over it specifically. If you want, you can go back and look at this. So this is the multiplicative rule. Here we're partitioning the probability of a positive, and again we get the same number. Negative predictive value can also be derived from that table. This were the number of negatives, right? The true negatives and the false negatives, and in that table, 98 were true negatives, so about 99% have a negative predictive value. So if the test is negative, that's the probability that you're not pregnant. We can use Bayes' theorem to calculate it. So given the test was negative, what's the probability that you're not pregnant? And then you can use that Bayes theorem and recalculate it. Okay, well, that's all for this chapter, and we'll start chapter 4 next time.